We do.
Okay, perfect. So I have the honor today to speak for Hazen and myself about Canada One Water and the phase 2 progress we're making on building this framework for groundwater surface water modeling and how it can support different applications. And this is, of course, a project that Hazen and I co-lead here, but we also have a third co-lead in private industry, Steve Fry, who contributes to this. And so we do have a big team. We've seen this a lot. We have all the people working on data input. We have land surface modeling happening that's concurrent to our 3D hydrogeosphere modeling that's happening. And then, of course, we have climate modeling and climate projections. And then we have our subject area specialists, so from different regions. And then we have our data delivery specialists. So a lot of people work on this. And I thank everyone for all the work we're doing here. So in this past fiscal year, what did we work on? There was a lot of work. We're still working on it to get all the data sets that we've compiled through this project published. And I'll speak a little bit towards that. We're getting progress made on modeling the water storage trends we see in Grace and doing that for 70 watersheds across Canada. I'll show a bit of that results. We're starting to do forecast in total water storage change, and I'll speak a little bit about that in the end. And then we're continuing to develop different applications of this model using nested models at higher resolution. I'll show some of that. And then we're making some progress in actually delivering some water indicators, and I'll speak about that at the end. So working on this dataset publication and engagement, we've now published the hydraulically parameterized integrated soil bedrock and peatlands dataset. That's in Data and Brief from Kessel. And then I just actually today had a nested model application published also in Data Brief. That's a Carcajou model. I can send a link to that later. But we also have a DTM that includes the full lake bathymetry that we use in Canada One Water. That's been submitted for publication, and we're about to submit the climate forcing data all to Data and Brief. And so this past year, there were about 11 conference presentations. So we're getting out and sharing that quite a bit. And we have 7 presentations upcoming under Canada One Water in this month. So more engagement's been happening. So a year ago at IAH, Hazen helped convene this panel on groundwater in the Canada Water Agency. We had Dr. Sonia Talwar on that, so our DG, and then the DG of policy at the CWA, Gemma Bog. So that was speaking about the public groundwater science and policy. And then Hazen started this work with Canadian Geographic as they were building this huge, and you can see it on the bottom here, floor map of water in Canada. And they wanted to include some components of groundwater. So then through that work, Hazen got me involved too, and they wanted to highlight some careers of people that work in water. So that's me sitting beside the QR code on this giant map. But I got to talk about my career in water, and it was me and a videographer that were featured kind of at the release of this map. So that was an exciting opportunity for us. So then I'll just spin this model here. Hazen was working on this TAP program project with Ethiopia for most of the year. And it culminated kind of in the fall, working with the GSC ourselves, Aquanti, and then this modeling company, Invitel Solutions, to co-develop a training program. And so 20 folks took it virtually from Ethiopia to learn about kind of water and groundwater modeling and building kind of these data frameworks. So then we had the kind of like privilege of having these 2 water scientists and instructors from Waterloo University, Asmar and Antone, visit us here for a week at the GSC. Hazen took them up towards Wakefield to look at some rock cuts here in the winter, and we got to learn a lot from them. So the thing that I learned, I think it's really valuable, is that they don't have the same industry that we have in Canada. So they don't have kind of this commercial mining or commercial well drilling or commercial geophysics. So they don't have the same opportunities to kind of train their students that we do. So it was really interesting to kind of discuss that and kind of the privilege that I've had being trained in Canada. Okay, so on to the science that we've been doing. I spoke earlier about how we're trying to model the Grace total water storage. So the Surveyor General, so John Crowley, provides us with a Grace solution for 70 large watersheds that cover all of continental Canada, the Canada One Water model domain. And then our Canada One Water portal, which is what we're showing on the screen here, it serves the results from 2002 to present. I say present asterisks, like the Grace satellite data comes to us with about a 3-month lag, and then we have a small lag getting stuff up onto the portal, but it's fairly recent. And so all these models we have results for all the 70 watersheds that go from 2002 to 2023. So it lets us look, like last year we were showing how well our models perform compared to surface water gauging stations, and this year we're showing them compared to this kind of satellite metric observation of total water storage. So I'll just show for, this is just a bit of a callback to last year, but we have kind of these 7 main models that cover all of continental Canada, and they're following the big watersheds in Canada. And so when we look at one, I'll just pick one to show you the GRACE results for, but this is the Nelson model. And you can see how it's been divided into these kind of sub watersheds. And then on the right here, we have the R squared value for every basin. And you can see it's pretty variable. So this is kind of where we've got the model results going to. We have kind of as high of an R squared value as 0.84. So that's pretty high, covering that whole kind of 20-year period. But then in some regions, it's a bit lower, so like less than 0.1. So there is room for improvement with these models. And I'll show you a bit of what that means. On the left here, this is watershed 6. It was that one that had a really high R squared value. And you can see for the whole kind of time period, black is the hydrogeosphere model. It's matching really closely to what the red, the Surveyor General solution for the GRACE satellite data is showing. So it's giving us the kind of interannual and seasonal trends, and then also giving us these kind of longer timescale trends. So the model's performing well. On the other side here, we have one of the zones where the R squared value is a little bit lower. And you can see kind of like earlier decades, we're under predicting kind of the amount of storage change. And then when we get to the end, it's over predicting. And so there's this kind of disconnect. And that's just one example where the model doesn't fit super well, where we still need to do work. There's lots of reasons this can happen. It's because whenever we model, we have to make these assumptions of what we need to include. And so by being able to compare like this, we can start to piece apart the areas where we might need to include more processes to get the model to match better. And the reason I'm showing this Nelson model is because we have this new opportunity. We have an alliance grant now with the University of Alberta and Dr. Brian Smerden to look at this model in particular and help us improve kind of process representation, geological representation, and see what we can do to make sure that all the watersheds in this kind of larger Nelson model are fitting to that GRACE forecast. Now, the reason that we're still working and getting this calibration or getting the model performance as good as we want, it's because the real objective and what we're currently working on and doing it concurrently is to run these models into future forecasts. So right now what we have is a 5-member ensemble that's completed using the CMIP6 with CRCM5 forcing. All that means is this is the CMIP, the global kind of climate model, and then it's been dynamically downscaled with this more regional climate model, CRCM5. And then we have 5 different kind of physics variations that lets us get a bit of an ensemble. What's running now is an additional 9 ensemble members. So we'll have a total of 14 that are running with CMIP6, but with the WRF dynamic downscaling. And that's just what's shown here. And so we're processing those results for surface water flow, so the flow at the gauging station, where we can compare it to what's been observed historically, and then total water storage, where we can compare it to historical GRACE solutions. Then we can kind of disaggregate that into surface and subsurface storage. So then we can really get to the point where we're looking at how groundwater storage might change in the future. So then here's just some of the basic results for that forecast that's been run so far. This is for the 5 ensemble members. So for each point, we have kind of the spread of the ensemble of the 5 different climate forcings available. And you can see the historical being the green here, and this is the Nelson on the left. You can see for every month at mid-century, the total water storage has decreased, is what we're forecasting. It's getting drier in the Nelson, and then it's not changing much, but maybe slightly wetter by end of century. So just some of that dynamics that we see. You can also see that with the uncertainty in the future forecast, we're actually getting a lot of overlap still among the different models. Then when we move to the Mackenzie, so it's a little bit of a different situation, but we still have this historical. There's a bit higher uncertainty in the historical in the Mackenzie, just because of the dynamics with snow and snow storage, but you have it getting wetter towards mid-century, and then kind of like some months, summer months being close. They're all overlapping within our kind of boundary of air, but it is generally getting wetter in the Mackenzie, or there's more water storage. So that's kind of the overall big picture work that we've been doing in using the models that we've built and seeing what they can tell us and trying to improve that. And then we've also been working on all these applications of the model. So now that we have all this data assembled, we're running the models, what can we do with it? Well, a big part of that was working with ECCC to look at ecosystem services. And so we were funded to test nested models within Canada One Water through the Canadian Wildlife Services Nature Smart Climate Solutions Fund. So this was looking at nature-based solutions to carbon emissions. And what they wanted to know is the effect of the ecosystem restoration, and they looked at both conservation, so keeping or securement or restoring, and how the water-based ecosystem services were affected by that. So it was really applying this huge framework to look at really refined models for site-specific assessment. So 8 sites, they had a total of 123, but 8 sites were collected, 4 were for restoration and 4 were securement. And they covered a whole variable kind of ecozone topography, all kinds of variables. The sites ranged in size quite on a large scale, so from 17 to 635 hectares. But to make this consistent and use this framework well, they all had a 50-meter maximum node spacing. So kind of the number of nodes, the size of the models varied depending on the kind of area that was being covered. So the models produced 5 key indicators of water-based ecosystem services like stream flow, infiltration, soil storage. And that allowed kind of efficient comparison between different restoration or conservation options. So allows quick comparison between sites. And then now after that was done to increase efficiency with ECCC, we've now moved towards developing a workflow to make 2D models. So instead of full 3D, just build a 2D model that lets the model run faster, quicker comparison, and it's being done for more sites. So finally, we started working with the Canadian Environmental Sustainability Indicators Group at ECCC because they would like to include a groundwater indicator in their water indicator kind of suite. Their indicators report change in previous years, so running our models can help that. So initially, we're looking at how we can use model or satellite-based observations, and then we work towards progressing a monitoring network to help support that. So that's the end, and that's always our links to our website and our portal if people want more information.
Thank you, Melissa. Sorry, you had 5 minutes, but by the time I realized I'd made a mistake, I didn't know how much time you had left. My apologies. So questions? Des questions pour Melissa? Questions for Melissa? From Paul, great work. CMIP6 has, like most climate model, a weakness in precipitation forecasting. How much is this uncertainty going to impact the climate forecasts?
Yeah, like we've done a lot of work, and I think what I showed with that GRACE comparison, the historical kind of validation period helps us look at what components work well, because we found that in certain areas we needed to use different snow models, that kind of thing. There's shortcomings in all of these, and so that's really part of Canada One Water is advancing that science. Like we're using WRF because of its like lake component and how that affects climate. But again, none of these are perfect. That's why we have the ensemble.